Cameras are cheap, lightweight, and ubiquitous, making them a popular choice for navigation. In this work, we aim to have an autonomous robot with a single RGB camera to navigate to a known goal in an unknown indoor environment. We adopt the learning-based waypoint navigation framework. It maps the current image, speed, and goal position to a waypoint using convolutional neural network. Then a model-based planner plans a smooth spline trajectory to the waypoint and generates control commands for the robot. However, due to CNN's prediction error, the robot often predicts deviated waypoint, which often lead to collision in narrow spaces. Also, the robot shows greedy behaviors and often cuts the corner. We hope to solve this problem by generating good training data using Hamilton-Jacobi reachability. HJ reachability is a formal method widely used in robotic safety. It uses first-order differential equation to describe the robot's dynamics, and disturbances can be added to account for uncertainties in the world like wind. In HJ reachability, we're focusing on computing reachable tubes to quantify the unsafe area within some time horizon that the agent has to avoid in order to guarantee safety. When generating training data, we use Stanford Large-Scale 3D Indoor Space Dataset. It contains 3D scans for 3 buildings, and we use 2 for data generation and 1 for testing. Given the map, we will first sample the start and goal position for navigation. Then, from the start, we design a reachability expert to deliberately choose waypoints until it reaches the goal, and collect current images, speed, and waypoint as training data. Thus, how to choose good waypoint given the current observation is the key factor of the training data quality, and thus affect the testing performances. We present a reachability expert for waypoint selection and trajectory generation, compared to the baseline methods. We propose a novel reachability cost, including time to reach and time to collision, to select good waypoints that consider both position, speed, and orientation. As a result, our robot can safely go through narrow openings. Besides, we use disturbances in the dynamics to model CNN's prediction error. As a result, the robot will stay in the middle of the road, which is more robust to CNN's prediction error as deviated waypoint. To compare, the baseline methods use heuristic cost. It only considers the distance to the goal and the distance to the obstacles, showing greedy behaviors and failing to enter narrow openings. Now, after we train a CNN on those training data, we run 200 simulation tests in new building in Stanford dataset. With our reachability cost, the robot has highest success rate and smoothest trajectory according to lowest acceleration and lowest jerk. Without disturbances, the robot takes the shortest time to reach the goal. However, the robustness of framework largely decreases. End-to-end learning is generally worse. For trajectory, similar performances are transferred from training to testing. For the baseline, the robot also shows greedy behavior and fails in narrow space. With reachability cost, our robot stays in the middle of the road and successfully enters the narrow doorway, which is only 70 centimeters wide. In our hardware experiment, we are using a Turbot 2 equipped with an Intel IntelliSense camera, and we only use the RGB image as input. All the computation is done with an onboard laptop with a GPU. The experiment is conducted in SFU building. The neural network is trained only in simulation and with no additional training or fine-tuning in real world. We can see that our robot can go through this narrow doorway and make a nice turn. To compare, the baseline method tends to be greedy and collide with the wall. Here are more scenarios that our methods successfully maneuver around cluttered environment where baseline cannot. In conclusion, we propose an automatic data generation methods to generate smooth, collision-free waypoint for navigation tasks via Hamilton-Jacobi reachability. By modeling disturbances in dynamics as same as prediction error, we enhance the robustness of learning framework. Immediate future work includes adding visual memory to the framework and include human agent in the environment. Thank you.